Before we move on to talking about the different types of electrical measurements that we're going to be looking at, I just want to briefly mention Appendix D in your textbook is an excellent resource. If you're rusty on oxidation numbers and how to find oxidation numbers for different compounds and things like that, and also balancing redox reactions, which can be a little tricky, not as simple as balancing most reactions. If you're rusty on those, go to Appendix D. We're not going to spend a lot of time in class talking about these unless you feel like you need some extra help with this. These should be things that you're already familiar with from general chemistry. We're going to focus more on the applications to analytical chemistry in this class. So anyway, just want to put a plug in that if you need some review, check out Appendix D. Okay, so when we're thinking about let's go over here. We're thinking about a redox reaction. We have, right, so if we take our iron and vanadium, for example, right, we have an electron leaving one species and going to another. So in this case, for this particular reaction, the electron is going from the vanadium to the iron. And this is a simplified picture here. We actually, need wires and an electrical circuit that will connect all of this. And we'll look at this in more detail as we continue through the chapter. But there are two different properties related to the electricity here that we can measure. So first is the current. And current is an amount of charge, or we can think of, amount of charge which is equivalent to a number of electrons passing a certain point in a given amount of time. So a current is a rate. It's the rate at which electrons are moving through the circuit. How much charge is passing through typically the end of the wire or something like that. And so this is generally measured in amps. Amperes is the unit, and an amp is equal to 1 coulomb per second. Coulomb is another unit that we need to define. Capital C is coulomb. I think I spelled that right. And this is a unit of charge. In chemistry, we often think about things in terms of molar quantities. So a coulomb is a unit of charge such that the electron has a charge of 1.602 times 10 to the negative 19 coulombs. And we call that E. That's the fundamental unit of charge. Now, as I mentioned, we often think about molar quantities. If we take Avogadro's number times E, that's equal to what's known as the Faraday constant. Sometimes you'll see this written as like a cursive F. I'm just going to write it as a regular F. And this is equal to 9.649 times 10 to the fourth coulomb. And again, this is called the Faraday constant. So this is how much charge there is in 1 mole of electrons. That's the simple way to think of this. Right, and so this is one of the things that we can measure, and this is what we would measure in analytical measurement, measuring amperometry. The other thing we can measure is voltage. Not voltage, voltage. And voltage is a measurement of electrical potential energy. And this comes from the fact in the circuit. And this comes from the fact that we have like charges pulling on each other. Right? So we have attraction here And so that creates a potential energy between the positive and negative parts of our electrical circuit. Or we have repulsion that are pushing things apart. Right, and so these are the fundamental forces involved in why there's potential energy involved in electrical circuits. And electrical potential energy is always measured as a difference, just as any potential energy has to be. So electrical potential is measured as a difference. So there's no such thing as just something is a voltage all by itself. It's always a difference, and it's measured in the unit of volts, which we write is capital V. And the way to think of this is a measurement of how much work is needed to move a charge through a circuit, or how much work can be done by that charge when it moves between a circuit. How much work is needed to move a charge or how much work can be done by a charge. And this, whether it is the work that's needed or the work that's done by the charge, has to do again with this attraction or repulsion. If there's an attractive force, then the charge can do work as it moves through the circuit. But if there's a repulsive force, you need to force the charge to go through the circuit, and you need to supply energy in some way. All right, so in the next video, we'll talk about what these two different measurements can tell us about chemical reactions.